Okay, hello everyone. Welcome to the 14th lecture and final lecture of 2020 for this class. So last time we proved bot periodicity, which I recall is the statement that the loop space of U is BU times Z. And we use that to define the spectrum KU, which is a very important spectrum and our first genuine example of a non-connective spectrum. Today, I want to give some examples about the cohomology theory and the properties of this spectrum. And so, recall, so if X is a finite space, we have that homotopy classes of maps from X plus, the suspension spectrum of X plus to KU are the same thing as pointed homotopy classes of maps from X plus to loops infinity KU, which remember is BU times Z. Sorry, pointed homotopy classes. And that's just homotopy classes of maps from X to BU times Z, which is just the Grothendieck group of vector bundles on X. And I'm not going to explain what happens when X is non-finite, but there is the description of that also in terms of vector bundles, so it's a bit more complicated. So I'd rather not enter into the details here. And then the other thing I want to say, okay, let me write KUN, sorry, of X for homotopy classes of maps from X plus to sigma n KU, which is the unreduced cohomology. And for X appointed space, the reduced cohomology is going to be, as you'd expect, classes. These are homotopy classes of maps in spectra. Okay, that's just notation. And okay, the other thing that we know is that the homotopy groups of KU are Z when star is even and 0 when star is odd. Okay. So, okay, so the first thing is that so there is a class beta in pi2 KU corresponding to 1. And remember, pi2 KU is the same thing as reduced KU0 of S2 by definition, homotopy classes of S from S2 to KU. And so the question, and this lives inside KU0 of S2, in fact, because KU0 of S2 is KU0 tilde of S2 plus KU0 of the point by the standard decomposition. Maybe I should put a remark here. KUN of X is KUN tilde of X plus, sorry, KUN of the point, as usual, as for ordinary cohomology. Maybe for ordinary cohomology, you this formula, you're used to see a formula like this, perhaps for n greater than 0, but that's just because in ordinary cohomology, the coefficients are 0 outside of 0. Well, here we have coefficients in all non-zero even degrees. Sorry, in all even degrees. So we have to keep track of them. But anyway, there is this beta here. And so this corresponds to some kind of vector bundle over S2, actually a formal difference of two vector bundles to be precise. And the first thing I want to do is to identify who this guy is. How can we describe it? And to do so, in the end, I decided to say something about clutching functions that I wasn't planning originally to say, but this should be quite easy. So first problem, let's identify beta as a vector bundle on S2. So to do so, let's talk about clutching functions. And one of the reasons why I decided to talk about it is that I realized that with the material that we have done, actually, it's easier than one might originally think. So the question, can we describe vector bundles over sigma x over some suspension? And well, the answer is yes, because we know that vector bundles of rank D over sigma x are the same thing as homotopy classes of maps from sigma x to BUD. Okay, that's easy. We are very tempted to go to move the sigma the other way. Unfortunately, sigma is not a left adjoint on spaces, only on pointed spaces, but we can fix this. So what is sigma x BUD star? This is vector bundles over sigma x together with a trivialization over the base point. That's because, if you recall, we have a fiber sequence. Sorry. This is something we saw last semester. I'm pretty sure I put this an exercise where this map is evaluation at the base point. I'm pretty sure I gave it as an exercise. Maybe last semester we say that this was a fibration and this is obviously a fiber. And so a point here is just a point here together with a path here from that to the base point. So that's literally what this is saying. It's a vector bundle on your space together with trivialization on the base point. And now this, we know by adjunction, is pointed homotopy classes of maps from X to UD. Actually, let me write it explicitly to omega BUD, which is from X to UD. And I want to describe actually how this correspondence works precisely. That is how from a map from X to UD, you can build a vector bundle on of sigma X. And and the reason why I'm doing this is because I'm thinking of S2 as sigma S1. And we want to start from a map from S1 to, well, it will be U1 and build a vector bundle there. Okay. Questions about what we're doing so far? So remember, a map from sigma x to BUD is the same thing as a coherent diagram x BUD. That's just the universal property of the suspension. But what does it mean? I mean, what is a pointed map here? Well, there's not much. It's just a trivial vector bundle of rank D over a point. Not much information there. And so its composition here corresponds to the trivial vector bundle of rank D over X. Let's pull back. We also can consider this composition here, which is a trivial vector bundle of rank D over X. Well, a different one a priori, of course, they're still the same, but then we give a homotopy here. And this homotopy corresponds to give an isomorphism of vector bundles. And note, this is not the identity in general. I'm just giving a general homotopy. If I have the identity, I would just get the constant map here. But I'm allowing different homotopies. So what this means is that this is phi from what did I call it? Oh, I think I might not have called it. Well, okay. X CD to X CD such that phi is an iso. Okay, it's an iso, but then I want phi to be the identity over the base point. That's just the fact that all these maps are pointed maps, and that the homotopy needs to be trivial over the base point. And so this is exactly the same thing as a map phi from X to UD. Okay, very good. But what does it mean concretely? Suppose I have such a map, so I can build, this coherent diagram. How do I build my vector bundle? Well, the idea is I want to see sigma x as the union of two copies of I wedge x. So concretely, this is with the base point identified, and I can see this upper piece as I wedge x, where I is the interval 0, 1 with base point, say, at one of the extremes. This is another copy of I wedge x, and they're glued together along a copy of x. That's just, if you want, this is contractible. So this is actually a homotopy push out because the inclusion of x inside this I wedge x is a cofibration, and so the strict push out is the homotopy push out. This is all stuff we saw last semester. And
Dennis, can you hold on for a minute? So is the do you mean pointed maps from sigma x to BUD? Are
yes,
they coherent diagrams?
Yes. Coherent diagrams in spaces, pointed spaces.
Can you recall, you said something about this fiber sequence somewhere above, that the pointed maps?
That was just to say that, I have this fiber sequence here. Well, this is just the standard inclusion, and this is evaluation at the base point. This is, okay, I wrote it for sigma x, but that's true actually for every y pointed spaces. And actually also here you can put whichever pointed space you want.
And this explains what you wrote above, that the homotopy classes of pointed maps are vector bundles. Can you explain again why you have the trivialization over the base point?
So, well, okay, in this case with BUD is actually super easy because BUD is simply connected. So it's going to be, you get a long exact sequence. Actually, let me write it here. I have a long exact sequence where you have pi1 of BUD, pi0 of map from, well, say y to BUD, map star, which is what we want to understand. This goes to pi0 map y to BUD. Oh, sorry, I think I might have messed up a little bit here. No, the trivialization should come from these, but this is simply connected. I mean, I wanted to identify this object here with the homotopy fiber of this map. And the homotopy fiber of this map is a point here, which I can think of as a vector bundle over y, together with a path here to the base point. Oh, I think I'm getting, this long exact sequence actually is confusing because it's telling us that the data of the trivialization of the base point is actually no data. It's contractible that comes from the simply connectedness on UD. But let me ignore the simply connectedness on UD.
Okay, yeah. Thank you.
Yeah, sorry. It turns out that up to homotopy, this is no data, but I would like to carry it along anyway, because I think it clarifies the difference, even if in this case, all trivializations are homotopic, because indeed UD is simply connected. So any path in UD is homotopic. But anyway, a point here is a point here together with a path downstairs from the image to the base point, which corresponds to the trivial vector bundle over the point. Okay, is this clear? Are there other questions about what I'm doing?
Yeah, so where is UD and BUD pointed? Is it?
Well, BUD is pointed by definition. It's a pointed space whose loop is UD.
Yeah, true. Yeah.
But if you want to think of it as the Grassmannian, I mean, doesn't matter. Pick any point. For example, I typically pick the inclusion of CD into C infinity as the base point of the Grassmannian if you want to use the Grassmannian model. It's not important. It's connected, so any base point will work. This is just a choice, a fairly natural choice I make. Okay. Okay, good. So, okay, what it boils down to here, you take, so if you replace this by I wedge X, and these are the base point of I wedge X, this recipe is telling you that to build a vector trivial vector bundle over this upper piece, let me call this I plus and I minus to distinguish them. They're homeomorphic, of course, but since I'm thinking of them as different. And I can take the trivial vector bundle over this guy, but then I'm gluing them over X times CD, well, using this map from X times CD to itself. So I have this map phi, let's say I'm gluing by the identity here and phi here. So to be precise, I'm taking the push out. Sorry, this is psi. Phi is a vector bundle over sigma x. It's clear this condition. This is how it's called the clutching function. You take two trivial vector bundles and you glue them along phi. And the non-triviality of phi in general gives you a non-trivial vector bundle. So why am I doing this? Well, because our goal, remember, was to identify beta in KU2 of S2. Now let's see how this works. So this is a class from S2 to BU times Z. And in fact, since beta is in KU tilde, is a pointed class. So it fits in particular inside BU times 0. And it has the property that when you adjoint it over once, you get a beta from S1 to omega BU, which is U. You should get the generator of pi 1 of U. Can we identify this generator of pi 1 of U? There is an obvious choice, and in fact it works. Because U1, remember, is exactly S1. U1 is the, well, it's the complex numbers of modulo 1. Just by definition, if you want, this is Z bar is 1. And this sits inside U, sending zeta to these matrices that are the identity everywhere except from zeta on the top left corner. And this is an S1. And I'm claiming that this map, this is a pointed map, of course, sends 1 to 1. In fact, it's a group homomorphism even. And I'm claiming that this map is the generator of pi 1 U. This is very natural. I'm sure all of you will believe it, but let me give you a very quick argument that I already hinted at last time. We have a fiber sequence like this that we studied also. I think I talked about it last semester, which sends a matrix A to A times E n plus 1. And the inclusion is B goes to B0, 0, 1. And this in particular tells you that this map is an isomorphism on pi 1 by the long exact sequence of homotopy groups. And so UN to UN plus 1 iso on pi 1. And so by induction, you get that the map from U1 to U is an iso on pi 1. Because you remember pi 1 commutes with filter colimits. And so we are done. So we know what the pi 1 of S1 is generated by the identity. That's pi 1 of S1 by okay. So beta from S2 to BU times Z corresponds to BU1 to the vector bundle, sorry, on U1 given by the identity. That is, we have on BU1, sorry, with clutching function the identity. No, sorry, that's what I mean. Oh, no. sorry, to the vector, to the map S1 to U given by Z goes to Z. Let me say it like this. Okay. Okay. And I claim, so we have a homeomorphism S2 with CP1, because both are, if you want, the one-point compactification of C. And this vector bundle is the tautological line bundle on CP1. So what it is, so let me define it for you. Psi is the pairs x comma L in C squared times CP1 such that x is in L. Here I'm identifying the points of CP1 with lines in C2. And I just want to say that these, under this homeomorphism, you can think of S1, sorry, S2 is sigma S1. And you can think of the copy of S1 inside sigma S1, that is CP1, as RP1 inside CP1. Right, you take, let me draw it, maybe this way is clearer. This is CP1, where I'm imagining the border all identified to a point. And I can find RP1 here. So this is the real axis, the compactified real axis inside CP1, and this gives me the suspension. And now I'm going to leave you as an exercise to compute the trivializations on these two half, in these two disks here. Here. And see that they differ exactly by the identity for the tautological bundle. That's not hard at this point. Everything is just writing down a formula and explicitly working it out. There is exercise. Compute the clutching function and see that it is the identity from S1 to S1. I actually did it, so I can actually, if you want me to write down all the formulas to compute the trivializations on these two half disks and etc. But I don't think it's very useful to see huge formulas on the board. Everything now is sufficiently explicit that you can indeed see it. And okay, so we're almost there. So we have a map from S2 to BU1, pointed map, adjoint to S1 equals to U1 into U. That's our map beta. But remember, this sits inside BU times Z as the zero component. So there are virtual vector bundles of rank 0. So while the vector bundle I constructed as rank 1, And why is that? Well, that's because I'm thinking, when I think of vector bundles of rank 1, these sits inside, these come from the map from BU1 times 1 inside BU times Z. So let me write it explicitly. Vector bundles of rank 1 come from BU1 times 1 inside BU times Z. Instead, I have it inside BU1 times 0. And how do you relate BU1 times 1 and BU1 times 0? Well, they're related by adding a copy of the trivial bundle. So beta corresponds to the virtual vector bundle, and I call it psi, right? Yes. Psi minus 1. By 1, I mean the trivial vector bundle of rank 1. On CP1. And that's what beta is. So, to boil down completely, KU0 S2 is Z plus KU0 tilde S2 Z times 1 plus Z times the class of psi minus 1. And that's the final point in the identification of the bot map, of the bot, element. Going to become the bot map in a second, but for now it's just an element on a group. Is this clear?
Sorry, how did you identify beta with this difference?
So beta is the pointed map adjointed. So beta seen as a map inside BU times 0 is the map adjoint to S1 from U1 to U. So in particular, beta comes from this composition from S2 to BU1 times 0 inside BU times 0. So in particular, this map is the map classifying the tautological bundle on S2, on CP1 actually. And the point, now I want to map these into BU times Z. Now remember, BU times Z was this colimit of disjoint union over N of BUN, where you add one copy of the trivial bundle. So BU times, so remember, you have BU times Z sits inside here. Okay, this is the identity. And at every point, this is essentially adding a copy of the trivial bundle, right? And I mean, my BU1 times 0 sits exactly inside here. It's not, it doesn't factor through to this factor here. This has only a BU0 that maps to BU times 0. So that's not very, this map in general sends BU n plus k inside BU times k at the nth stage. Right. And so we have so what I want to say, yeah. So, okay, I guess what I want to say is that what it boils down to is that beta plus 1 is exactly the class of psi. Because beta plus 1 sits inside is an element in BU times 1 that comes exactly from BU1 times 1 from psi in B1 times 1, right? Because if you have beta here and you add 1 to that, you end up exactly in this class of rank 1. I mean, essentially, the point is that beta has rank 0. It's a vector bundle, virtual vector bundle of rank 0 because it sits inside Ku tilde 0 of S2. And you can always get a vector bundle of a virtual rank 0 by taking a vector bundle of whichever rank you have and you subtract the rank. That's a fairly harmless operation. And that's exactly what's happening here. I have to describe this virtual vector bundle of rank 0 and then describing it as a line bundle, so a virtual vector bundle of rank 1 minus 1. And that's as explicit as you can hope to get. I mean, of course, it's not going to come from an actual vector bundle of rank 0 unless it's a trivial bundle. Because BU0 is just a point. There are no many vector bundles of rank 0. Oh, sorry, that's not the one I want to memorize. Okay. Is this computation clear? Because that's the bedrock on which we will build all the subsequent computations. Okay. The next thing I want to say is that Ku star is in fact a multiplicative cohomology theory. And I wish I had time to do the whole story of infinity ring spectra, but I don't. So I'll do a patch and just say what a homotopy ring spectrum is. And that's going to have to be enough for now. It's going to be precise and it's going to give all the structure we need for now, but of course, to do proper things, one would need more. So, okay, a homotopy ring spectrum is a spectrum E together with maps unit from S to E and multiplication from E tensor E to E such that, so let's see, the usual things you'd expect. Multiplication is unital and it's associative. And here I'm just saying that homotopies exist. That's why it's called a homotopy ring spectrum. I'm not specifying higher homotopies. So let me put a remark. To get, in general, to get a good theory, one would need to specify higher homotopies. The corresponding object is called an E-infinity ring. An E1 ring, because this is just an associative ring. It's going to be E-infinity when we throw in all the higher homotopies for commutativity. But we won't have time to talk about those. Unfortunately, I wish we had, but for now, let me say, okay, and say E homotopy ring spectrum is commutative if mu is the same as mu tensor sigma, where sigma from E tensor E to E tensor E is the swap map that we have. Remember, we always have an equivalence of E tensor F with S tensor E. We've seen that back when we defined the tensor product. And we're asking that, well, that's exactly what commutativity ought to mean, right?
Question. So can only connective ring spectra be connective spectra be ring spectra? So is the addition?
No. In fact, I would put a ring spectrum structure on Ku, which is very far from commutative. Sorry, from connective.
Because I mean the definition here per se just looks like it's a monoid, like with multiplication. So
yes, but this is the tensor product in spectra. Sorry, maybe I should be more precise. This is like when you define a ring as a monoid in abelian groups with respect to the tensor product in abelian groups. But I defined for you a tensor product in spectra. So now this definition.
Okay, yeah, but because we can also take non-connective spectra, this is, yeah, it's somehow weird. It's more than a ring because I don't have a group structure.
Yes. I know there is this mismatch between spectra and commutative mono and commutative groups that we discussed. I wish I could give you some deeper intuition about what this means. I cannot really. I mean, this is like working the difference between, you know, positively graded chain complexes and all chain complexes. And sometimes you have to work with all chain complexes. I mean, that's just something you have to do if you want the theory to work better. And we do want, because Ku is a very powerful and important gadget, and it is very far from connective. So, where was I? Yes. Okay, so now put a remark. If E is a commutative homotopy ring spectrum, the associated cohomology theory is multiplicative. Because that is, there are maps am I going in the right direction? Yes. So, okay, actually, let me be precise. Pi star of E is a ring. No, actually, sorry. Let me say it this way. E star of X smash Y has a map from E star of X tensored over Z to E star of Y. No, of course, the map goes in the other direction because it's a ring. Jeez. Not a core ring. And how does it work? Well, remember, this is homotopy classes of pointed maps from, say, X to sigma n of E, and this is, say, homotopy classes of maps from Y to sigma infinity of X, sigma infinity of Y. And then I want a map from sigma infinity of X smash Y, but that's, remember, is sigma infinity of X tensor sigma infinity of Y. And then you can map it to sigma n E tensor sigma m E. Just by taking, if you take F here and G here, you can take F tensor G. And that's just sigma n plus m of E tensor E, and then you use your multiplication to get the composition that we want. And also we have maps, well, okay. You have a map E star of S0, a point 1, and that's corresponding by eta from sigma infinity S0 to E. And these satisfy all the multiplicativity and commutativity if you have a commutativity relation that you want. In particular, E star x plus, so unreduced cohomology for X and unpointed space, is a graded ring. Commutative if E is commutative. And that's because you get a map. What was it? X plus tensor X plus, like in ordinary cohomology, you get a map here to the wedge product of this thing, which remember is just X times X plus. And you can pre-compose with the diagonal. And this gives you a ring structure. There are, of course, associativity and exciter relations to be verified. Sorry, not commutative. That's force of habit. Of course, I meant graded commutative, since this is in graded abelian groups. And the graded commutativity actually comes from the fact that the antipodal map on S2 is multiplication by -1 on homotopy groups, which is well, okay. Which I'm sure everyone can prove it. Okay, so why did I mention this homotopy ring spectrum? Is because Ku is 1. So proposition Ku star, okay, sorry, Ku is a homotopy commutative ring spectrum. And okay, and the proof is going to depend on a choice, unfortunately. In fact, the choice is not going to be a choice at all, because all the choices will be homotopic. In fact, there's going to be a contractible space of choices. And so all the multiplication maps I'm going to give you are homotopic. But this is, in this ambiguity, actually hits the complexity of the notion of infinite ring spectrum that I'm sidestepping. So let me make a choice. Let us choose an isometry C infinity tensor C infinity over C with C infinity. For example, a bijection of n times n with n. And then you send EI tensor EJ to E, I don't know, phi EJ. For example, it's not necessarily, in fact, the space of such bijections is not to be contractible, but the space of such isometries is. So I'm just fixing. Let me call it phi, such an isometry. Then I get a natural transformation like this. Where V was that infinity space that I used to define Ku. So remember, points are eupole of vector spaces in C infinity, and this is J upo, and I can send this to, well, I want to send it to VI tensor WJ. But of course, this is not a subspace of C infinity, it's a space of C infinity, tensor C infinity. So I have to fix it with this isometry. And that's why I need the isometry. And again, the space of such isometry is contractible. It's essentially the same proof as the case of the Stiefel, as the contractibility of the Stiefel manifold. So it turns out not to matter, because of course, if two isometries are homotopic, this map is also homotopic. This is a natural transformation of functors, so natural transformation in E plus and J plus. And moreover, if you look at how you define B of V as an infinity space, this yields B to the n, V I plus, B to the n, V J plus, mapping to B to the n plus n. Remember, B was just defined. B of I plus is just the geometric realization of VI plus smash gap n plus. That was our definition. So you can just add a smash gap n here, a smash gap n, and then you go by induction, and you every time you can add a b on each of the factors here, as long as you add a b here by naturality. And in fact, oh, maybe I should have said it better. This is in fact a smash. That is, I define a map from the product, but if you put just the base point, which is just the zero vector space here, of course you get the zero vector space on the target. I mean, the base point on VI plus is just the I pole, while all VIs are the zero vector space. And so if you tensor, you get the zero vector space again. Okay. And so we can get a map from the colimit omega n sigma infinity bn v omega n. No, sorry. So remember, this was b infinity of v. And the colimit of omega m sigma infinity bm of v is b infinity of v again. And so b infinity of v tensor b infinity of v is the colimit over n from omega n plus m sigma infinity bn of v smash bm of v. Because the tensor product commutes with colimits in each variable and commutes also with loops, because we proved it. And so we get a map, the colimit over nm omega m plus m bm plus m v, which is b infinity of v again. Now maybe I should give a name of this guy. This guy is usually called the little ku, and is indeed the connective cover little ku is the connective cover of big ku. That is, it's the connective spectrum with the same omega infinity. That's just by definition, pretty much. And so we have shown that little ku is a homotopy ring spectrum. In fact, I haven't shown you, but of course this map is also symmetric using the symmetry of the tensor product. So in fact, this is going to show that it's a homotopy commutative ring spectrum. But remember, we didn't want little ku, we wanted big ku. So what we want is how to go from little ku to big ku. And now, but pi 2, since ku is the connective cover of big ku, we have pi 2 ku is still the same as pi 2 of big ku, which is z generated by the bot element. So the bot element is a map, if you want, from sigma 2 of s to little ku. And I want to say that big ku is obtained from little ku by inverting it. And what do I mean? I mean that big ku is the co-limit of this sequence of maps. Where this map is obtained by, well, okay, this is s times ku, which maps with sigma minus 2 ku tensor ku, and here with the multiplication. Okay. Maybe I should stop 1 second because I think I'm going quite fast. So is it clear how do I construct the ring structure on little ku? And to be completely honest to you, I am skipping a bunch of checks that all the diagrams I'm writing actually commute. That I gave you explicit definitions of all the maps, so hopefully this won't feel too much like cheating, because the checks are just, unwrapping what these definitions are and see that they indeed commute. Okay. And then I want to prove this claim, and this claim is going to imply that big ku is indeed a homotopy ring spectrum as well. Why is that? Well, because if assuming this claim, then ku, tensor ku, can be written down as, well, actually a colimit of a square diagram, but I'm going to take the diagonal. Like this. and then you can map it into KU. By the multiplication at every step. This might look a bit confusing, but if you look at the definition if you look at the proof, so this is like the proof that R with X inverted is a ring. For X a ring. The elements here, an element here should be thought of like Y over beta square, for example. It's like a fraction. That's actually literally true on the homotopy groups. But okay, so now let us prove the claim. The proof of the claim is actually not hard. It's basically, again, about periodicity. I mean, it's basically how I defined KU secretly. Big KU. Because big KU, so remember, let's look at little KU. Little KU as a spectrum starts with BU times Z as before. Then it takes its delooping, which is U. It's connected delooping, and then it takes its simply connected delooping, which is, however, BU. And then you take its connected delooping of that guy, which is SU. And go on. And the previous ones are not, sorry, the following ones are not as explicit. But I only care about here, up to here. So sigma 2KU then is what do I want to say? Yeah, U is shifts on the right. And here actually there is an BU. Shift 2 steps on the right. Remember, sigma was a shift. Sorry, the sigma minus 2 is the same thing as omega 2. I think I said that at some point I will use sigma minus 1 as omegas in spectrum. And this map beta is, well, it's the identity here, and here is the inclusion of the connected component. And here is, well, the inclusion of the subgroup. Whatever. The next one, actually, for what it's worth, I think it's BSU. Yeah, of course, it's BSU. The next one. But it's not important. Again, look at this column. This is actually the universal cover of this space, if you want.
So the KU downstairs is a big KU?
No, this is a little KU. So I have a map beta from sigma minus 2S to KU, which corresponds to picking out pi 0, 1 in pi 0 of BU here. And then considering this map KU, sorry, sigma 2, no, sorry. Yes, by, what do I want to say? Yeah, sorry. by 2 bu times z, sorry. It's corresponding to this map. Maybe I should say by 1 of u, whatever, that's probably easier. And by 1, I actually don't mean the generator. I mean, this is a z, and I don't mean the trivial element. I mean the generator of the z, which is by 1 of u. And so I can consider the map. I can see this as a map also from S to sigma minus 2 of Ku, which is what I actually wanted to say. Yes. And so I can consider the map from Ku, which is S tensor Ku, to sigma minus 2 of Ku tensor Ku. Take sigma minus 2 of the multiplication, goes to sigma minus 2 of Ku. This is beta times 1. Is multiplying by the bot element, which is the bot map.
Now I'm just confused because sigma minus 2 Ku should just be a shift by 2 of Ku.
Yes, which is what this is. A shift on the right.
But
I mean, I'm starting at 0, but actually secretly there is a -1, -2, and etc., which are not very interesting because they're just copies of u and bu times z. Actually, let me, maybe this is clear if I number how these things work. 0, 1, 2, 3, 4. And let me add. The -1, -2. And you see that the bottom line is the top line shifted on the right twice by 2. And I'm claiming that this map is, well, it's not a very interesting map downstairs, but the point is that we know, for example, that this element here is the this is the connected the looping of u, and so it's bu by definition. And we know that this map here, bu times z, map at level 2, has to be the map actually, it's probably clearer. It's probably not very clear because this u here, I'm already secretly using bot periodicity to describe it. I'm using the fact that bot periodicity u is b of bu times z. And this map is the, sorry. I guess it's the point is that the map at level 1, is the equivalence of b bu times z, which is actually what I should have written at level 1 in b infinity, mapping to u. And we know that we have an equivalence, which is beta, which is the map coming from the bot periodicity. And that's the map I'm using. Only I'm secretly identifying b of bu times z with u, and so I'm saying that the map is the identity. This might be confusing, perhaps. The point is that this map, I'm claiming that this map is this map. And why is this claim sensible? Well, because Ku to sigma minus 2 of Ku is a map from a connective spectrum to another spectrum. And so by the universal property of the connective cover, these factors through the connective cover, Ku to t greater or equal than 0, sigma infinity minus 2 of Ku. But I'm claiming that what periodicity is telling us is that this is Ku again. Because the omega infinity of sigma minus 2 of Ku is just omega 2 of Bu times Z, which by periodicity is Bu times Z again, which is the omega infinity of Ku. And this map multiplication by beta is exactly the map corresponding to the identity here. Because it is, well, because it is this map. Beta is defined as to be this map secretly. And not secretly, explicitly even. And so you can see now, if you look at this map beta, and you apply it again, shifted and shifted, this is all making my diagram shift on the right, like here. So when you go to infinity, just U and Bu times Z cover everything. So you'll end up with big Ku. So at the limit, the spaces of calling Ku sigma minus 2 Ku sigma minus 4 Ku, etc., are exactly those we used to define big Ku. And so, well, and so we are done. Okay, why did I want to say that big Ku is a multiplicative cohomology theory? Except that it, it is interesting. And okay, remark, looking at the definition, the ring structure on Ku0 of X is given by tensoring of vector bundles. That's how it is. Oh, and maybe I didn't define what a tensoring of a vector bundle is actually, but it is what you expect. So if you have vector bundles P E to B and P prime E prime to B, you can form E tensor E prime as well, the vector bundle whose fiber over B in B is the tensoring over C of the fibers of E and D prime. And this actually makes sense because you can look at local trivializations. Or if you want, you can say that's universal for bilinear maps, just as the usual tensor product of vector bundles, vector spaces. And okay. And the reason why I said that is because proposition, I want to say what Ku tilde star of S2n is. Ku tilde star of S2n is just Z generated by this class that generated Ku tilde 0. Ku tilde 0 of S2, but then you tensor itself to the n, you take the nth power. So I'm using this ring structure to deduce. So remember, we had a map from Ku tilde 0 S2 tensor, Ku tilde 0 of S2 coming to Ku tilde 0 of S2 smash 2 is to the n. So this is what it is. Essentially I'm claiming that this map is an equivalence, is an isomorphism. And to do that, I'm going to prove a stronger statement. I'm going to prove that this map is an isomorphism for every x, this multiplication map. And this proof might surprise you because it's very, oh, sorry, not x, sigma 2x, of course. And the proof is, well, this is a map of cohomology theories. Right? Because this is just a Z secretly. So the left-hand side is non-canonical, well, even canonically just Ku tilde star of x. And the right-hand side is just precomposing with the suspension, which also preserves all the structure of cohomology theories. So it corresponds to a map of spectra, which is, remember, this is just Ku tilde star of x. So this is a map of spectra from Ku to sigma minus 2 of Ku, since these are the spectra representing the cohomology theories. Because maps from sigma infinity sigma to x Ku tilde is the same thing as maps from sigma infinity x sigma minus 2 Ku tilde. And if you look at what this map is, this was the multiplication map. So this is again the multiplication by beta map from Ku to sigma minus 2 of Ku. But Ku is defined exactly so that this map is an equivalence. So okay, one last computation. And we are done, I think. Questions about this argument? This is slightly trickier. This is slightly cheaty in some sense. Normally, I'll be honest, normally the proofs of Bott periodicity go through proving that this map is an isomorphism for every x and deducing Bott periodicity out of it. I'm doing it backwards compared to the usual story. but well, I like this argument, and I wanted to present it to you. Okay. Let me finish with the latest computation, which is Ku tilde star of CPN. And I claim that this is Ku tilde star plus Ku tilde star of psi minus 1. That was for CP1. Then you need to add psi minus 1 square Ku tilde star psi minus 1 to the n as a, sorry, as a, no, sorry, not tilde. Why am I putting it? Tilde. I don't want tilde. As a Ku star module. And these, you should think of it as the analog of the formula that the cohomology of CPN is Z plus ZX plus ZX to the n in classical cohomology. And remember, in the ring structure, actually here you prove that it's Z to the n modulo xn, x to the n plus 1. Here it's not going to be true anymore that the n plus 1 power of this is trivial. It's going to be a linear combination of some of the other things. But I don't want to write it because it's, well, I mean, I could, but okay. Let me not. So the proof is by induction on n. And you start, the idea is to consider this cofiber sequence. Cofiber sequence S2 to the n. So if you think about it, Cp to the n is some kind of compactification of C to the n with exactly a Cpn minus 1 at infinity. So if you want, this is the map sending x to 0 dot x. And so if I collapse the whole part at infinity, I'm just left with an Sn. This is, if you want, the standard cell structure on CPN. And so we get a sequence. So CPN, KU2I, KU2I, CPN minus 1, mapping to KU2I plus 1, S2 to the n. And these gets a map from KU2I of S to the n, and gets a map from KU2I minus 1, CPN minus 1. That's just the long exact sequence in cohomology. And now this is 0 and this is 0. These by the CPN minus 1 by induction, and these by the computation we already did. And this is Z times this bot class to the n. And up to, oh, sorry, I want the reduced cohomology here. So otherwise it's not 0, of course, it's the one of the point. So by induction, we have that this is Z psi minus 1 z psi I1 minus 1 to the n minus 1. And so, in fact, this is split because this has a section, because all these free basis elements lift, because the tautological bundle of CPN, of course, restricts to the tautological bundle of CPN minus 1. So we know that essentially we have shown that this object, sorry, up to n minus 1 plus a term, which is just a z by the previous computation. And so the only thing we need to verify is that psi minus 1 to the n restricts to the generator of ku tilde 0 s2n. That is, it's trivial on CPN minus 1, and okay, that we knew, but and it restricts to this generator on ku0 sn. And the way to do that is to notice that you have a commutative diagram like that. Oh, sorry, S2. Well, okay, the right vertical map is just a collapse map that kills off the CPN minus 1. This map is just, again, the collapse map that collapses everything but the top cell. If you want, this is the wedge. So we collapse. And this map is actually the slightly trickier one. This is the symmetrization map, which, let's see. If I write this as A1, B1, AN, BN, this is sending me to the coefficients of the polynomial A1 plus B1x, AN plus BNX. So this is a degree n polynomial, so you get n plus 1 coefficients, and you write them in order, and it gives you a point of CPN. That's you can of course write the formulas if you want, but it's and you have to check that in fact this is this commutes. But the point is that you have to in this vertical map here you have to kill all elements that have a base point in one of the factors, and the base point in one of the factors is correspond to choosing 0, 1. And if you have 0, 1 here in some of the factors, the constant term here is trivial, and so this gets killed by this collapse map. It lands into CPN minus 1. So in fact, this diagram does commute. Okay, you have to check that the other maps are as you'd expect. I guess you have to check because you have to choose an equivalence like this, and an homeomorphism of S2n with this mesh product so that this works. But the point is that this map is a homeomorphism outside of when you remove, all the pieces containing a base point here, because every polynomial has a unique factorization. So you can see. And okay, I'm out of time, so let me just say, you take the generator here, of ku tilde S2n, and you want to say that when you pull it back to here, you get the tautological bundle. Sorry, you get the nth power of the tautological bundle. And what you actually show is that when you pull it back all the way here to this product of CP1s, you get the tensor power of the tautological bundle of each, over each of the factors. And that you can do along this map. And you see that it is indeed what you want. And okay, I think I don't have time to give more details. And sorry if this was a bit unstructured, this class, but well, I hope it was interesting anyway. And then we'll start in January with rationalizations, inverting primes, completion of spectra, and all sorts of things. And we will use K-theory as an example in this story. And after that, we'll finally start talking about Atiyah duality, which is the spectral version of Poincare duality for general cohomology theories, and then Thom's theorem on the classification of manifolds up to Bortism. And I don't know if we'll have time to do more than that. If we will, I might do a very brief introduction to spectral sequences, but no promises there. We see how much time. I absolutely want to do the two things I described, and see how much time we have left afterwards. Okay. Questions?
So if you consider this Ku reduced sigma n, then you get some cohomology theory. Does it have some like naive interpretation?
Ku tilde?
Yeah, Ku tilde.
Ku tilde, well, Ku tilde is two periodic, so there is not much to be said. Ku tilde I of x is Ku tilde 0 of x, which if you notice are virtual vector bundles with rank 0 over the base point. So that's clear. When clear, as clear and geometric as these things come. And then if I is even, and pointed maps from x to u if I is odd, which I don't know if it's clear or not. I don't have a better description, but hopefully this is like. Oh, and the point is that if x is compact, sorry, this is all. If x is compact, is just union of pointed maps from x to un. So you can think of a map as, I don't know, associating a matrix. You can think of these, I don't know, automorphisms of x times cn of the trivial vector bundle of rank n. That preserve the trivial, that are the identity over the base point, sorry, because they're still reduced. I don't know if that's geometric or not. This is as geometric as these things come, though. I mean, you don't get much more. In fact, it is an open problem for a different cohomology theory that's somehow analog to Ku, actually to Ko more than Ku, which is called TMF. It is still an open problem to construct such a geometric description. People will be very interested in having such a thing, because that cohomology theory has very nice properties, but of course, nice properties as a cohomology theory are sometimes not enough. You sometimes also want to understand what it means. And for K-theory, we lucked out. We have a very explicit description in these terms. I don't know if that's explicit enough for you, Joachim.
Mm-hmm. Well, maybe another question then. Slightly more general, I guess. So I very much enjoyed the E-infinity groups, and I was wondering, would you like to put some references in the notes about where to look about E-infinity rings? If you don't want,
infinity rings.
if you don't want
That's
to
a
cover them.
difficult question. Yeah, I am going to put references in the notes. Unfortunately, I know only two types of references. Classical references that I find extremely hard to read, and more modern references that require a lot of prerequisites, which is why in the end I decided not to talk about infinity rings, even if I would have liked to, because it would require me to actually properly construct the symmetric model structure on spectra, like with all precision and details, and then define what a ring is in spectra in a symmetric model infinity category, which is not the hardest, but it is a bit abstract, honestly. The alternative is that, okay, to be, I'll put it in the notes, but to put it briefly, the three references I would give are, so there is a paper by May, what are infinity ring spaces and infinity ring spectra, which is on the classical side. It's one of the first papers in which these things were defined, which I find extremely hard to read. But you do see the connection with isometries and isometric embeddings and so on and so forth. And the book by Stefan Schwede, which is already in the general references, covers this material, even if so briefly. And of course, for the modern approach, there is higher algebra, which is very clean, but also very demanding on a technical level. I mean, the name higher algebra is of the whole book is essentially a study of higher ring structures, but it's very technically demanding. The point is that we didn't want to define what an infinity operand is, because it would take a while. Oh, also actually a good introductory reference, somehow orthogonal thing, which I might add, there are these notes by Jonathan Harpaz, which gave a class in Paris 13 a couple of years ago while I was there, where he gave us somehow a geodesic path. His goal was to talk about factorization homology, which uses essentially infinity rings and so on. And I think he strikes a good balance between giving all the details and trying to aim at a definite goal, which is good. Actually, yeah, I should add those notes. Those notes are good. I should add those notes as references. Okay.
Okay, thanks.
Okay. Are there any other questions? If not, Merry Christmas to you all, and hopefully we will meet each other in 2021. Fingers crossed if this doesn't get any worse.